Hello, everyone. My name is Rick Frage. I'm the sales manager at SFTec Incorporated. On behalf of our team, I'd like to welcome you today to this webinar, our eighth webinar, about um, designing flat plate with CSI safe software. This webinar is presented by Dr. Ahmed Salama, who will be explaining the details of how to maneuver with the software. So a little bit about Dr. Ahmed Salama. Dr. Ahmed Salama is a structural design expert at SFTec Incorporated in Montreal, Canada. He has served as a bridge engineer at the Egyptian Ministry of Water Resources and Irrigation, where he supervised different construction phases of several different bridges. Later on, he worked as a bridge design engineer for short span bridges that were constructed over the Nile River. Afterwards, he decided to continue his education, so he came to Canada and he continued his PhD studies at the University of Sherbrooke under the supervision of Dr. Ibrahim Ben Mukran. During his PhD studies, Dr. Salama tested full-scale edge slab column connections, which were extracted from a prototype of GFRP RC flat plate parking structure. These tests aimed at simulating the real case of such connections, quantifying the behavior and strength of such connections, and finally introducing new formula for the FRP design standard in Canada and USA. Which are the ACI 440.1R-15 for the USA and the CSA S80612 for the Canadian standards. So Dr. Ahmed Salam also contributed to the CSA certificate tests of different FRP materials for different manufacturers in Canada, USA, Germany, and China, under, of course, the supervision of Professor Ibrahim Ben Mukran at the University of Sherbrooke. So this webinar, I'll be doing the introduction. We will discuss a little bit of some field applications of fiberglass rebar. Then I'll hand the mic to Dr. Ahmed to do some analysis and explain some analysis of GFRP RC flat plates for parking garages. And we also will do a design of GFRP flat plates for parking garages. We have our branded product are mostly designed in Canada here and then manufactured in China by Shandong Safety Industry in Shandong, who are specialized in the production and manufacturing of fiber reinforced polymer products. So we work with national and international engineering firms. We work with them through the design process. We help them design and get acquainted with FRP standards, whether they're in Canada or the US. We try to focus our energy and effort on parking facilities, water treatment plants, and retaining walls. Our focus basically is on the GFRP bar applications, and mostly there is the bars. However, we do have other products like the sheets and the AR mix for the concrete mixes. So FRP material composition, it's simple. As we can see here, it's basically the fiber and resin, which is a polymer. And also we have an interface between them, and they are connected together and put together through a process of pultrusion. So what you are seeing here is a microscopic view of an FRP bar. So the different types of FRP and how they compare to steel. As most of you know already, we have different types of FRP. We have more than what's listed here. We have glass, aramid, carbon, basalt. However, those are the three main or more popular fibers. And if you compare them to steel, you will notice two things: that glass, being the least strong between the three, the aramid and carbon, is already 2 or 3 times has better resistance to stress than steel. So it has a 3 times the tensile properties of steel. And also the second thing you will notice is that they are linear up to failure, while steel yields, it has ductility. So our products, we are capable of producing different types of FRP products. We produce FRP bars, spirals, connectors, bent bars, and whatever shapes you will need. The most popular, of course, of these products is definitely the bars. However, the most popular fiber is the glass out of the 3 listed before. And the reason being is that, as I explained before, it has already doubled the tensile or tripled the tensile strength of steel. However, it's the cheapest in terms of cost, in terms of budget, compared to carbon and aramid. So that's why GFRP glass fiber polymers are the most popular in the market today. Some of the advantages of SFT bars or GFRP bars instead of steel or over steel. Basically, it has a longer service life because of its corrosion resistance. So it has an improved durability in harsh marine conditions. So it's perfect for ports, construction, or any building or walls that are whether in touch with the marine, with the water, or very close to considered marine environment. There usually you have more corrosion. The advantageous corrosion resistance, it goes back to that. So if you compare to steel would corrode, and FRP in general does not corrode no matter what. It has greater tensile strength, as we saw before. It is at least 3 times stronger than steel. However, even though it's stronger than steel, it is 1/5 the weight of steel, which makes it easier to work with, safer and faster. The fact that it is corrosion proof makes it perfect for chemical environments also. So if you're doing mining industry is a perfect example, pipelines or water purification stations and so on. And finally, it's neutral to electric and magnetic disturbance, which makes it perfect also for applications like airports, military applications, MRI rooms in hospitals and so on. Some examples of FRP. We have a lot of projects across the world. We chose a few to show you. One of the projects is here in Canada, which is the first waffle slab designed with FRP bars, with SFT bars. So that was built in Nova Scotia, in Halifax, Nova Scotia last year. And those are some pictures of it. Also, it can be used for slab on grades. It's a perfect, if it's a non-structural slab, it's a one-to-one replacement, no need for complications, and it will save you a lot of money compared to steel, not only on the price of bar to bar, but also in terms of labor and everything involved, delivery and so on. Another project to show is this is an IBM building. So they did cast on site walls, and they used our our FRP bars. This project was built in China. And to the right is a retaining wall built for the city of Montreal. They designed a retaining wall to dump some snow in winter for the de-icing operations and so on. So they created this retaining wall. And what's better than FRP to resist all these de-icing harsh chemicals that are added on the street? So that's why they used our SFT bars. So that's it. That's my role. I'll hand the mic to Dr. Ahmed to explain a little bit more about how to design flat plates with the CSI safe software. Sir Ahmed, mic is yours.
Thank you so much, Rick, for this great introduction. And hello again to everyone here in our webinar. In the next slides, I'm going to talk about a numerical example for a flooring slabs of 2-story parking garage. And this flooring slab of 2-story parking garage is located here in Quebec, Canada. As we see here, this is the dimensions we receive, from the guy who designed the slab with steel bars. And they asked to design this slab with FRP in order to see the difference in the cost and other stuff. So we received the dimensions of the slab thickness of 250 millimeter. And here the loads are very, very high. So the designer decided to put a drop panel around the column, as we see here, The thickness of the drop panel is 200 millimeter. All columns we have here in this flooring slab is 300 by 600 millimeter. So, and also the wall thickness. In the boundary here of the slab, we have walls, and you can see the walls here with the blue color. So all the boundary here, we have here wall on this boundary. The thickness of this wall is 250 millimeter also. So what I'm going to do is to create the DXF file as known by all engineers who are using the CSI safe software. Here it should be CSI safe. So the first thing I created the model on CSI safe software, and after that I'm going to talk in the next slide about the input data. So here the slab thickness, I put the slab thickness 250 millimeter. The drop panel defined here the slab with drop panel and the columns wall thickness. So let us see how I did that. Actually, we received some data. We have given data for this slab. So the concrete strength for the slabs equal 35 MPa. Based on the concrete strength, I'm going to calculate the concrete properties, like the elastic modulus of concrete EC. EC, according to the Canadian standard 823.3 equals 4,500 by the square root of FC dash. So EC equals 26,622 MPa, and the FCR equals 0.6 by the square root of FC dash also. So F crack here equals 3.55 MPa. Alpha 1 and beta 1, the factors of flexure. So here alpha 1 and beta 1 can be calculated using this equation based on the given FC dash. So by substituting FC dash in this equation and that one, so here we have alpha 1 equals 0.8 and beta 1 equals 0.88. As we talked before on our plan, the concrete dimensions for the slab and the slab thickness equals 250 millimeter. The drop panel thickness equals 200, and the clear concrete cover for the bars equal 30 millimeter. And actually we're gonna check this one also based on the bar we are using, because the clear concrete cover in the Canadian standard CSA S806 is a factor in the bar diameter. So if you are going to use bar diameter of 10 millimeter, bar diameter of 15, 20. So the concrete cover will be gonna change from a value to another value. And also the designer give us, the service and ultimate loads. And actually, because we are here designing this building in Canada, so the loads were specified according to the National Building Code of Canada, NBCC, to the year 2015. The dead load here equals 5.15, live loads equals 12, and you can get this value from the National Building Code according to the type of the structure. So if the type of the structure is like residential building, this value will be less. This value is very, very high, because we talking about parking garage and heavy loads. And also here we have snow loads, and also this value was calculated according to the equation in the National Building Code of Canada. So here the snow load equals 3.44 kilonewton per meter square, and the rain load equals 0.4 kilonewton per meter square. So as known, we have a lot of loading cases, but we are going to select the factored load case, factored load combination, and the service load combination that will govern our design. So here W factored equals 1.25 times W dead load, which is 5.15, plus 1.5 by W live load, which is 12 kilonewton per meter square. And here we are going to add a part for the snow load. So the snow load here is 3.44, and no factors here will be used for the snow loads, so it will be 1. So finally, the WF equals 27.9 kilonewton per meter square, while here the WS, which is W service load, will be equal W dead load, W live load, and a part of snow load. So WS equals 17.12 kilonewton per meter square. At this point, we are going to assume some data in order to go in our design. So for the reinforcements that we are going to use in our slab, actually as a preliminary suggestion, I suppose to use GFRP SFT bar number 7, number 6, and number 5. And between the brackets here, you are going to see the bar diameter for each one. Here is the bar diameter of number 7 is 22 millimeter, number 6 20 millimeter, and number 5 is 16 millimeter. Also here you can see the area, the cross-sectional area, for number 7, number 6, number 5. And actually this area is taken from the Canadian standard S807 for the specification of FRP bars. And actually in our factory we are respecting to have bar diameter with the nominal diameter of this bar, like 22 millimeter for number 7, for number 6 20 millimeter, for number 5 also 16. So finally here we have also the tensile properties, and these tensile properties in terms of the ultimate strength, the elastic modulus, and ultimate strain, these properties were determined according to the Canadian standard CSA S807 after testing like 3 lots from each bar size. So we have here for number 7, we should test 3 lots, different lots from each bar size for number 7, number 6, number 5, in order to have these values. And as we see here, the tensile strength is 1250, elastic modulus 65,000 MPa, and the ultimate strain equals 0.00185, and we are gonna use this data in the design. So here, as we see, after creating the model in the CSI SAFE 2016, and by the way, this program can be used for design of slabs, beams, foundations, and also for post-tensioned concrete. If you have post-tension concrete slab or other stuff like this, this is a suitable program you can use from as we do in our office. So as we see here, this is the 3D view of the model. So here we have the walls on the boundaries, as I mentioned in my first slide for this example. And here we have the column with the drop panel. We have the drop panel slab here, and we have the column, and we have also the slab of 250 millimeter thickness. So after creating, the model, we need to check that everything is fine, and the thickness of the walls, the slabs, everything should be defined properly as given by the designer or as assumed by you as a designer. So after getting to the analysis step using the CSI SAFE software, we have our slabs, and we can get from the program the moment distribution in X direction. And actually you will see in the program M11. So M11 here means the moment distribution in the X direction. So as we see here, we have some colors, and these colors give us the value of the bending moment distribution in our flooring slabs. So as we see here, this color, which is the most common one, is ranging from 0 to 100. So this color, I mean this one, as we see here, this one is ranging from 0 to 100. And actually this color representing the moments, the positive moments in the middle is bands. Here we have the column, and here also we have the column. This moment here is the negative moment over our columns. However, The other parts, as I said, the most common color here is for the positive moment, which is ranging from 0 to 100 kilonewton meter. And after that, we're gonna see here we have a spot, and this spot is ranging from 100 to 200, which is the next level. So what I'm going to do here is to take a range of 100 kilonewton for the most parts of the slab, and we're gonna check how many bars that I'm going to use to design this slab. And for this spot, I'm going to try to put additional reinforcements. But if I'm going to design this slab totally, for this higher value, it will cost us high and high value of money, high and high value, of time also. So what I'm going to do is to unify this area with a uniform mesh, and for this one I will put additional reinforcements. So let us talk now. We talked about the moment distribution in X direction, so let us talk about the moment distribution in Y direction. In the program you will see the term of M22. So here, as before, here we have a color, and as we see here, this color is the most common one here in the flooring slabs, and this also for the positive moment. So here the positive moment is ranging also from 0 to 100. So it seems that we are going to have a uniform mesh in both directions. So we are going to take M ultimate positive for the uniform mesh to be 100 kilonewton. However, we can see here another spot which is little bit higher. It's heavy green, and this heavy green area is ranging from 100 to 200. And also we have here a heavy green area which is ranging also from 100 to 200. As I said in the previous slide, we are going to put additional reinforcement in this area in order to cover the higher moment that is ranging from 100 to 200. So in step number 4, we are going to select the bottom reinforcement in X and Y direction. And as we see, the most common spots in the X and Y direction carrying the range from 0 to 100. So I took the range 100 kilonewton meter for the moment. So we are going to see how many bars are needed to cover this moment. So as I did here, we are going to assume a bottom uniform reinforcement mesh, 6 bars number 5, and number 5 here is 16 millimeter. So I'm going to use 6 bars per meter. So 6 by the area of 1 bar. So the AF here total will be 1194 millimeter square. And also we need to estimate the effective flexural depth in both orthogonal directions. In the X direction, we have slab thickness minus cover minus 0.5 D bar. So we are going to use 16 millimeter. So D 0.5 D bar will be 8 millimeter. And we have here the cover of 30 millimeter. So 250 minus 38, it will give us 212 millimeter. However, DY will be TS minus cover minus 1.5 D bar. And DY will be 196 millimeter. As I mentioned in our first webinar for the design of flat plates using GFRP bars, I mentioned that we should check the failure mode. So here we have the area reinforcement in 1 meter, and we have the depth, the flexural depth in X direction and in Y direction. So we are going to use this data in order to calculate the flexural reinforcement ratio in X and also the flexural reinforcement in Y. The flexural reinforcement ratio here in X equals 0.0056 and in Y 0.0061. And in order to check the failure modes, we need to calculate the balanced flexural reinforcement ratio. And actually the balanced flexural reinforcement ratio, according to the Canadian code CSA S806, can be calculated using this equation. In this equation, we have all data known. We have alpha 1, we calculated before, and beta 1, phi C, and phi FRB. And here we have FC dash and FF ultimates, epsilon concrete ultimate, and ultimate tensile strength. So finally, the flexural reinforcement ratio balanced 1 will be 0.0027. And as we know from our previous webinars, that if the flexural reinforcement ratio, which is this one or this one, is greater than the balanced flexural reinforcement ratio, so the section is compression controlled section. And actually, the compression controlled section is the most preferable section in the case of using GFRP bars or any kind of FRP bars. So here we check the failure mode and it's okay. Continuing to the selection of the bottom reinforcement, we are going to calculate the neutral axis depth. So here we are going to equalizing the compression force with the tension force. So the compression force from concrete will equal the tension force from the GFRP bars. So here, the compression force will be this term and the tension force will be this one. And we have here C, which is a neutral axis depth. And also we have C on the other side. So finally C equals 45.95 millimeters. Right now we can calculate the MR. MR here is the resistance moment. The resistance moments can be calculated easily using this equation. So here the resisting moment equals 141, while the factored moment, if we remember, it's 100. So here we have 141, so it's a little bit higher, but it's safe. So here also we have a check for C over D. C over D equals, should be greater than 7 over 7 plus 2000 by the epsilon FRB ultimate. So here C over D is greater than this value, which is okay. In step number 5, I would like to talk about the selection criteria for the top reinforcement in the X and Y direction. As known, the top reinforcements will be selected in order to cover the negative moment in our slab. So here we are using the same criteria as I explained for the bottom reinforcement in order to select the top reinforcement. And we are going to add additional bars over the column as we did for the bottom reinforcement if it requires to be added. Sometimes when you design this kind of slabs, no need to add the additional reinforcement for the top and the bottom. But you know, it's rare to add bottom additional reinforcement, but it's normal to add top additional reinforcements in many cases that I did before. So I already face a lot of cases for adding additional top reinforcement. So now we designed our slab in X and Y direction and selected the bottom reinforcement. So here we need to check the serviceability limit state in order to make our design completed. So as I mentioned also in the theoretical webinars I did before, how we can check the serviceability limit state for any flexural member. So here for the serviceability limit state, we have two steps. The first step here is called the stress and strain limitation. So we are going to check the stress and the strain in the used bar under service loads. From the analysis, MS, which is the service moment, equals 55.60 for one of the critical sections. Here we have as a flexural reinforcement ratio, and also NF, which is the ratio between the elastic modulus of the FRB, which is EF, to the elastic modulus of the concrete. So in F here equals 2.44. So rho F by NF will be 0.012. So we are going to calculate factor called K. So K will be depends on rho F by NF. So by substituting the value of rho F by NF, you will get the value of the factor K. And here also we are going to calculate J, which is 1 minus K over 3. So J here equals 0.95, which is the lever arm between the compression and tension forces. So here in this equation, we are going to calculate the stress. So FFS here is the stress in the bar under full service loads. So by substituting with the moments, and here is the area of reinforcement area, AF. Here is J, which is the lever arm. And here is D, 212, here is D. So FFS here equals 233 MPa. The code requires that the stress in the bar under full service loads to be less than or equal 25% of the ultimate strength. So here FFS equals 233, which is less than 312 MPa. So this one is okay. Actually, the elastic modulus of our rebar is known from testing, and we calculated right now the stress. So we know the stress under full service load, we know the elastic modulus, so easily we can calculate the strain. So here the strain will be the stress over the elastic modulus. So here the strain equals 0.0036. And actually this value is greater than 0.015. So when you have this value is greater than 0.0015, you should go to the step number 2 in the checking of the serviceability limit state. However, if you are designing a concrete structure with FRB bars and your ultimate strain under full service load is less than this value, so no need to go to the next step. However, when you have the strain in your bar under full service load greater than 0.0015, so it is the time to check a factor called Z. So Z is the crack width parameter. The crack width parameter Z can be calculated using this equation. And we have two limitations of Z. This limitation for the exterior exposure. We have here parking garage, and this one will be outside, you will not have any, it's called like exterior exposure. You will have exterior exposure. So for the exterior exposure, you will compare this limit by 38,000. However, when you have interior exposure, this factor equals 42,000 Newton per millimeter. As we see here, we have some factors to be determined in order to get the value of Z. So here we have KB, and KB is a factor depending on the surface finishing of the bar. So here we are going to use hand-coated GFRP bars. So the factor KB will be 0.8. So here ES, and here is EF. So ES is the elastic modulus of the steel, and EF is the elastic modulus of FRB. So here is 200 over 65. FFS, which is the stress under full service loads. So the stress from the previous calculations equal to 133. DC is a factor which equals the TS minus D. So the slab thickness minus the effective flexural depth. So DC equals 38. According to the code limitations, DC should be less than or equal 50. So if you are going to calculate DC, and found that DC is greater than 50. So forget about the calculated value and use 50. So here DC equals 38. So we are going to take it 38. And also here for the factor A. The factor A here equals 2 by B by DC over the number of bars. So here this one should be 38, not 40. This one should be, I'm sorry for this mistake. This one should be 38. So this one, the factor A, which is the last factor we are going to calculate in this equation. The factor A equals 2 by B. B is the width of the strip. So we took a strip of 1 meter width. DC calculated from this equation, and we assumed using 6 bars number 5. So number of 6 in 1 meter is, in our strip, is 6. So here A equals 12,667 millimeter. So by substituting using the above, the previously explained and the calculated terms here, the value of Z equals 46,511. And actually this value is greater than 38,000 Newton over millimeter. So this one is unsafe. And also this one should be greater than. So this one is unsafe. So we need to make it safe in order to have a safe design. Without serviceability limit state, it checks, your design is nothing. So I decided here to increase the number of bars to 7 bars. Again, we are going to calculate the stress. The stress here equals 198, and this value is less than 0.25 by the ultimate strength of the bar, ultimate tensile strength. So this one is okay. And the factor A in the Z equation here is changed to be 10,857 millimeter square. So again, by substituting with the new values of FFS and A, the value of Z factor equals 36,283. And actually this value is less than 38,000. So our design right now is safe. So thank you so much for continuing with me until reaching the end of the presentation. And actually, I would like to thank Rick and other colleagues whom contributed to SFTec. And thanks a lot to all of you again.